Welcome to our demo of Sawmill, a system that can take users from logs to causal diagnosis of large systems. Failures are common in large systems, and the theory of causality can help us respond to them effectively. Diagnosing failures in production is notoriously challenging. There is not enough time for classic debugging approaches like testing, formal verification, or simulation. Instead, operators have to work backwards from observational data collected from the system at the time of failure. Diagnosis might be the first step, but these teams are ultimately interested in going beyond it. They want to alert the appropriate engineering team in order to repair the system. Whenever there are multiple ways to fix a problem, they would like to identify the most efficient way to utilize engineering time and effort. The theory of causality can help quantify and compare the impact of different possible interventions with the system, helping operators in their task. However, there is an important mismatch at play. Operators often only have access to logs, semi-structured textual chronological accounts of key events. However, causal inference requires inputs in a different format. It requires a table of variable values for each of a collection of causal units, for example sessions, and a causal model of how these variables affect each other, often represented as a causal graph. Sawmill can help bridge the gap between these two representations, ultimately making causal inference based on logs possible. In our demonstration, we will first showcase Sawmill's capabilities to SIGMOD attendees using real Postgres logs. After selecting the right file, the preview tile lets users inspect a snippet. As we see, this log file involves users setting different parameters, like the amount of work in memory, before executing the TPCDS workload for scale factor 1. Let's use Sawmill to analyze these logs and find out how the adjusted parameters affect mean query latency. To begin, Sawmill transforms logs into a preliminary tabular representation called the parse table. Users can specify arguments to the drain log parsing algorithm, which is used to separate log templates, the fixed part of each log line, from the so-called parsed variables. We can inspect the templates, as well as the parsed variables on the right. Sawmill uses large language models to generate a human-understandable tag for each parsed variable. Log parsing can be challenging, and even a state-of-the-art algorithm can sometimes identify a part of the template as a variable. For example, Drain has created a single variable for each of the parameters we tweaked in Postgres, with another single variable capturing all of their values together. In our framework, users can correct such errors using the next interface, by specifying the appropriate misparsed variable. As we see now after this call, the system has generated 6 different variables, one for each of the parameters. Moving on, users can restructure the information in the parse table along the lines of causal units they're interested in. For example, they can specify that values in each session should be aggregated, providing the session ID, and then calling prepare. This yields another tabular representation, the prepared table, with 1 row per causal unit and 1 column per aggregated variable. Sawmill chooses which aggregate to use for each variable in a way that maximizes the empirical entropy of the resulting values, thus preserving as much information as possible. At this point, we have created a tabular dataset out of logs, but we're still missing the causal modeling. We'll use Sawmill to derive that next through a novel process called Exploration-based Causal Discovery. In this process, users can specify a target variable of interest, like the mean duration of a query. Sawmill will then return a list of curated candidate causes based on the prepared table. Here, it identifies 11 candidate causes out of dozens of variables in the prepared table. If the user is unsure about the semantics of one of these variables, they can use this next interface to inspect it. This will print some information about the variable, information about the template that contained it, as well as example values from the prepared table. The user can then leverage the domain expertise to filter out the variables that really could affect mean query duration out of this curated list, things like the amount of work in memory or the max parallel workers, as opposed to things like the date and time that the log was collected at. They can then start constructing the causal model by adding the appropriate edges one by one and building the graph interactively. Here, we can add an edge for each of the 6 variables we identified and incrementally build the graph on the right. Sawmill also provides interfaces to explicitly reject irrelevant edges from causal graph inclusion. The graph will be dynamically updated on the right as users add more edges. After building the model, the user can pose average treatment effect or AT queries to Sawmill. For example, the user can ask for the AT of the max parallel workers parameter on the mean duration of a query. Once the user specifies their query, the result will be printed on the left. As we can see, this effect is surprising since it appears positive, as if adding parallelism would lead to higher query latency. This is an indication that the user might need to spend more time in exploration-based causal discovery, something also evident from the low exploration score as calculated by Sawmill. Thankfully, Sawmill provides users with the best variable to explore next, which users can do by returning to the first interface. Here, exploring candidate causes for max parallel workers surprisingly reveals that the setting of workmem is the top candidate cause with a negative coefficient. It seems like some confounding is present, whereby more parallelism is only enabled when restricting each worker's working memory. The user can then add the associated edge to their causal graph. This will update the graph and also the AT on the left, which now appears negative as expected. To ensure no further confounding is present, users can continue following Sawmill's exploration suggestions and work on the graph until the exploration score reaches 1. After walking SIGMOD attendees through this demo scenario, we'll give them the opportunity to independently use Sawmill to pause and correctly answer AT questions over additional logs, with known causal effects but varying difficulty in terms of noisiness and confounding. Thank you for your attention.